If a machine seeks a keyword, it searches a rigid grid, but human knowledge doesn't exist on a grid. It exists in fluid, overlapping concepts. Traditional relational databases are built for exact matches. They scan rows and columns for specific text strings or numbers. But when you ask a generative AI to synthesize ideas or understand the nuance in a complex prompt, those scalar structures break down. The machine doesn't need to find a matching word. It needs to understand the meaning behind them. This requires a different mathematical unit of memory, the vector embedding. Large language models generate these embeddings to carry deep semantic meaning, plotting data across thousands of dimensions so that related concepts physically cluster together in space. Mapping and comparing coordinates across thousands of dimensions requires immense computational power. If you force a traditional database to calculate the mathematical distance between every point in this dense space, the system simply chokes. It wasn't built for similarity math. To give generative AI a reliable, scalable, long-term memory, we can't modify old infrastructure. We have to build a new environment designed natively for high-dimensional mathematics, the vector database. Many engineers initially try to solve this by pulling a standalone algorithmic index off the shelf, like FICE, and treating it as a complete solution. A bare index is a search algorithm. It lacks the operational layers required to run software. You can't easily update records, manage horizontal scaling, or handle fault tolerance. To productionize AI, a standalone index is insufficient. We have to construct a complete vector database from the ground up. That process requires taking the dense mathematical core, wrapping it in standard database operations, and eventually decoupling the entire system into a serverless infrastructure. Without these operational layers, a raw index is just a script running in memory. It lacks the concurrency controls and state management required to handle live updates and high traffic. At scale, this leads to memory exhaustion and unrecoverable data loss. Imagine a dataset with 1 billion parameters. Calculating the exact mathematical distance between your query and every single vector in that space, in real time, is computationally impossible. The solution is approximate nearest neighbor, or ANN search. By trading a marginal fraction of perfect accuracy, the system achieves extreme query velocity. This velocity relies on a lossy compression algorithm called product quantization. This visual shows a single, high-dimensional vector array. To shrink its memory footprint, the algorithm first splits the long array into smaller, distinct segments. Next is the training phase. The algorithm uses k-means clustering to build a codebook for each segment. This creates a pool of representative cluster centers. During the encoding phase, the system discards the heavy, exact coordinates of the vector segments, swapping them out for lightweight ID codes from that codebook. When a user submits a query, the system maps the search against these compressed codes rather than the original massive data structure. Product quantization provides the essential compression layer, keeping the sheer weight of high-dimensional AI data from overwhelming system memory limits. Once the data is compressed, the database needs a way to navigate it quickly. This is handled by a hierarchical navigable small world algorithm, or HNSW. Instead of storing vectors in a flat list, HNSW builds a multi-tiered graph. Here, we see vectors clustered into isolated nodes on different vertical layers. The system evaluates the clusters and draws connecting edges. That similarity is determined at the node level using strict mathematical metrics, typically measuring the cosine similarity of the angles between vectors, or their straight-line Euclidean distance. When a query enters the database, it hits the top layer of the graph and follows the edges down. It bypasses massive portions of the dataset entirely to find the closest match. By converting an exhaustive linear scan into an efficient geometric tree traversal, HNSW mathematically guarantees rapid retrieval. Mathematical speed handles the vectors, but in an enterprise application, raw vectors require operational context, metadata tags like authors, dates, or product categories. To manage this, a complete vector database maintains 2 separate indexes side by side, one for the vector math and one for the metadata. Reconciling these 2 indexes creates a bottleneck. The system decides whether to filter metadata before or after the vector search. Here we see pre-filtering on the left and post-filtering on the right. With pre-filtering, the system reduces the search space up front. but this risks completely dropping highly relevant semantic matches from the calculation before they are considered. Post-filtering guarantees semantic accuracy. However, it forces the system to perform heavy math on the entire dataset, only to discard irrelevant results at the end, creating massive compute latency. Managing the trade-off between these two indexes requires a query optimizer and a control plane. A standalone algorithm executes the search, but lets the logic to coordinate separate systems, which is why a dedicated database wrapper is required for enterprise scale. Even with a complete database wrapper, first-generation vector architectures have a critical flaw. HNSW and PQ algorithms require constant, massive memory allocation to stay ready. If compute and storage are tightly coupled in a monolithic architecture, companies pay for peak-level computing 24/7, even when queries are idle. A serverless architecture solves this by separating the index storage from compute instances. Storage sits quietly until compute is specifically required. To execute this separation, the system uses geometric partitioning to break the main index into smaller subindices. This allows the database to boot up compute strictly for the specific partition needed by a query. But partitioning introduces a new latency. Geometric partitioning is a slow background process. Newly ingested vectors are hidden from live queries while the index is being built, creating a freshness problem. To ensure new data is immediately accessible, the architecture inserts a dedicated freshness layer. This acts as a fast, temporary cache that new vectors bypass the main partitions to reach. A query router sends incoming searches to both the index and this freshness layer simultaneously. Once the main index finishes building, the vectors flush from the temporary cache into permanent storage. Decoupling storage from compute and adding a freshness layer allows vector databases to scale elastically. The AI now maintains an instantly updated, cost-optimized context window. Let's trace a query in this serverless environment. The router splits the request, checking the freshness cache and the partitioned index. Inside the storage block, it reads compressed codes and traverses the HNSW graph tree, finding semantic proximity instantly. At the exact same time, the operational layer processes the query, balancing the mathematical cosine distance against strict metadata filters to refine and isolate the precise subset of data required. This robust, multi-layered cloud architecture executes massive workloads that the simple script of an open-source index simply cannot sustain. This design enables massive multi-tenancy. It safely isolates completely different workloads on the exact same hardware, scaling up instantly based on usage metrics. A vector database is a purpose-built, high-performance computation engine, providing the specific memory architecture necessary to scale artificial intelligence.